Hi guys, so let's continue where we left off. Now we've been considering permanent changes that are introduced to our crystalline system, and one of the best example or one of the example that we considered in our previous session was a bent wheel or the bent rim of the wheel. So what we essentially mean by that is you have a metallic system wherein the atoms occupy specific positions. And these specific positions are primarily because these atoms exist in the force field, and the forces experienced by the atoms innately, without any external disturbances, depend on the positions of the atoms. Now, to such a system wherein the force experienced by the atom depends on its position, you are imposing an external force. So, in our case of the bent rim, let's say somebody stomped on it, let's say applied a load to it. So you are exposing such a crystalline system to that of an external force. The combination of these two forces, which is expressed here, depends on the position of the system altogether. Now this gives us a relation, a mathematical relation, which can be expressed as an equation of this form here. Now when we solve this equation, this second order ordinary differential equation, we end up knowing the positions of the atoms. Now when you know the positions of the atoms, it becomes possible for us to understand how the atoms have dislocated from their original position, meaning it becomes possible for us to describe the dislocation of the atoms that ultimately translate to the permanent damage that we observe in our wheel. So by solving this equation, we are essentially able to understand or describe mathematically the permanent damage that the wheel has experienced. So what we will attempt to do in this session, in the upcoming ones, we will not primarily try to solve this equation here, but rather we will try to build a tool that will help us solve this equation. So even though our starting point is to solve this equation here, what we ideally want to do is we want to build a tool that will help us not only solve this equation but other similar equations of this form here. So other similar equations meaning equations that are ordinary differential equations. So again, the goal is not a solution but a tool. So the reason I want to emphasize or reiterate this is because when we are building a tool, we are going to deviate from the primary problem statement that is mentioned here. We are going to move away from this primary problem statement that we have posed ourselves, so that we are able to build a tool that is versatile and can be applicable for similar expressions. So to put it in a different context, instead of just trying to find the easiest route from your classroom to your hostel, you are just exploring the areas that surround your hostel and your classroom, so that irrespective of what your mood is and irrespective of what the climatic condition is or irrespective of where you are with respect to your hostel, you are able to safely reach the hostel. So that is what our goal is. We just don't want to have a solution which will be restrictive. We want to build a tool. So when you want to build our tool, when you want to end up having a tool, it means we have to go away or move away from this specific problem that we have stated. So please bear with upcoming few aspects of the upcoming session. It might seem that we are digressing, but ultimately all these digressions will end up solving this and similar expressions. Now, when we want to generalize this expression here, we don't want to restrict ourselves just to solve for the positions of the atoms. We want to have a generalized expression which is in this term. Now, when I want to have an expression that involves not just the positions of the atom, but rather a general function of f of x, now this expression here then can be translated to something like the second derivative of my function with respect to my variable is equal to, let's say, a and f of x. So when I translate this, to a generalized expression, I end up having something like this, where A in this case could be the ratio of my K and M. M is my mass and K is the proportionality constant. So this is the constant that remains, and the entire expression now is expressed using a generalized function, not the position of the atoms. Now this and these two expressions here are equivalent in the mathematical framework, and if I'm able to solve this, then basically I'm able to solve this as well. So if I have a tool to solve this, I'll be able to solve this as well. Now when I solve this expression here, I end up having the position of the atom x of t, and when similarly when I solve this expression here, I end up having f of x, the function that satisfy this expression here. So this is rather vital for us to understand at the very outset, that is when we are solving a numerical expression that has physical significance, we need to understand what exactly are we solving for. When we get a solution out of it, what is going to be the physical significance of it. In the earlier case, we had a numerical expression, we solved for it, we ended up having or ascertaining the positions of the atoms. In this case, we have a generalized expression, and when we solve it, this is what we would end up having. Now, one way of solving such an expression is taking the double integral. Of course, that is something that pops up to our mind when we consider the relation between integration and differentiation. But this is rather not so ideal approach or not so versatile approach. Now, what we are going to see could be an alternate for such a restrictive solution, and that is why we are interested in, because we want to develop a tool that is versatile. We want to develop, as the name indicates, as a tool, as opposed to the term being used in our dictionary. This tool is, of course, hugely useful to us and can be used in different scenarios. We don't want to restrict ourselves to a specific one. Now, this being our solution that we are interested in, we want to find the f of x that satisfy this equation here. We begin by assuming that this solution is smooth and can be expressed in this way. We have an equation, and this equation, and the solution for this equation can be expressed. The solution for this equation can be expressed as a function. This is an equation or a relation that we want to solve, and the solution for this equation can be expressed as a function, and we begin by considering that this solution is a smooth one. And this assumption, we assume that my solution is smooth, and this assumption here, this my solution is smooth, allows me to write my solution in this form. So I assume that this solution f of x, which is expressed in this way, is the solution for my original equation. And now when I am able to find out, so this is my variable x, the primary variable, and now if I am able to find out the unknowns in this expression, that is a0, a1, a2 and a3 and so on and so forth, in view of this mathematical relation here, then I will be able to come up with a solution that will satisfy this expression here. So let me repeat, I have a mathematical relation that stems from my materials study, and this mathematical equation is something that I'm interested to solve. And as opposed to taking a conventional route, I understand what is going to be the nature of my solution. I try to attempt to understand what is my solution is going to be. I understand that this solution is going to be a function. I assume that this function is smooth, and correspondingly I expand this smooth function in this way. So this is what we refer to as the power series expansion. Since I have assumed that my function is smooth, I have expanded my function, which is the solution of my expression, as a power series. And in this power series, there are two terms that are involved. One is the variable x, and the other is the coefficients a0, a1, a2 and a3 and so on and so forth. Now when I'm able to calculate or ascertain my coefficient in view of this expression that I have developed, then I have a solution that satisfies my original equations. So this is the approach that we were trying to take when we are trying to solve such equations that we have developed. Now the power series expansion can be expressed in this way, using the summation notation. Now when I want to find out these coefficients, let's begin by considering A0. The A0 can be known when I substitute my x is equal to 0. When I assume that my x is 0, that gives me an expression for my A0. This is something that we have considered as initial condition. So basically the first term, the first coefficient can be understood, or the initial condition, it corresponds to the first term, and it can be ascertained by considering my variable to be 0. Now let me move on to the second term. An expression for the second term can be arrived at by considering the first derivative of the original power series. When I want to arrive at the second term, I begin by taking the first derivative of the original power series, and then I substitute my x equal to 0. I take the first derivative and then I substitute my x as 0, and I end up having an expression for my second term, that is A1. A0 is my initial condition. A1 or A0 is when I substitute all my x's to be 0. When I make all these terms to be 0, I end up having my A0. Now to arrive at A1, I take the first derivative of my f of x, and then I turn all the other terms to 0 by substituting my x as 0. Now this gives me A1. Now when I want to understand or arrive at what A2 is, then I take the second derivative of my f of x and substitute my x equal to 0. That will give me A2. So my A1 is the first derivative of my power series, and substituting x equal to 0, my A2 is the second derivative of the power series, and this ends up with giving me 2A2. Now this can be extended for to understand or to know what my A3 is. When I take the third derivative and substitute my x equal to 0, I end up with an equation like this, which gives me my A3 is 1/6 of my third derivative. So I have an equation. The solution for the equation is a function. I assume that the function is a smooth function. This allows me to write the solution in the form of a power series, and in the power series, when I'm able to find out my coefficients, I end up with a solution. To find out my coefficient, I first substitute my x equal to 0, that gives me A0, the first coefficient, and I take the first derivative of my power series, substitute 0, that gives me the second term. Second derivative, substitute 0, another term pops up. Third derivative, substitute 0, another term pops up, and this I can continue, and I would end up having an expression for and a value for a known value for A0, A1, A2, A3. So I will end up having a value for all these unknown coefficients based on my derivative of the function. Now when I substitute this, when I substitute or replace my coefficient with respect to the derivative of my function, I end up having an expression like this. And this expression is what we refer to as Taylor series. So we have power series wherein we assume that the solution of my original equation is smooth, and when I'm replacing the coefficient of the power series with the derivatives of the function, that allows me to calculate the coefficient, I end up having the Taylor series. It is vital to note that I take the derivative and then substitute the x with 0, and that is what each of these terms mean. So each of these terms, it means that I have a function, and in that function my x is 0. In this case, the function is the third derivative. In this case, the function is the second derivative, and in this case the function is first derivative. In this case, it's the original function, and I'm substituting my x is 0. So when I do that, I end up having a Taylor series, a solution, a Taylor series which is nothing but the solution, which is based on the f of x, which includes or that introduces the relevance to my original function. Now again, it is also again, this being an undergrad course, it is also vital for me to expose you guys to the different ways this particular Taylor series can be written. So one other way of expressing this Taylor series is in this way, wherein we take the first derivative and introduce x equal to 0. So first derivative at position x equal to 0, the second derivative at position x equal to 0, the third derivative at position x equal to 0, the fourth derivative at position x equal to 0, f of x at x equal to 0. So this is another way of writing the same expression above. Both these are equivalent. There is also another way of doing it. Again, we should not confuse this with substituting 0 and taking the derivative. This, when it is as clear as this, as a Taylor series, what this means is we are taking the first derivative and then substituting 0. Second derivative, substituting 0, third derivative, and so on and so forth. So the Taylor series can be expressed in these different ways. And now it is one elegant way of rewriting this expression is when you replace these fractions, particularly the denominators of these fractions, you end up having the factorial values. So this is one of the elegant way of expressing the Taylor series. So basically, to give you a quick overview or review, so we have an expression, an equation rather, and this equation has a material significance. We have come up with this equation based on our understanding of the material, and when we want to solve this equation, you end up having a function. We assume that the function is smooth, and since the function is smooth, we are able to express it as a power series, and the coefficient of these power series, which is unknown to us, we understand it by taking the derivative of the power series. We take the derivative and substitute it to 0, we end up having ascertaining or determining the coefficient, and this is what we refer to as the Taylor series solution. Now, the reason we made the assumption that our function or the solution f of x is smooth, because when we take the derivative, first derivative, second derivative, and so on and so forth, our function should be differentiable. Meaning, if our functions are not differentiable, if this f of x is not differentiable, if it is not smooth, then our power series or Taylor series expansion becomes restrictive, and we won't be able to efficiently use this approach. So that's the reason we start off with the assumption that the solution for our expression is smooth, meaning we are allowed to take. So what's the meaning of smooth here is we are allowed to take several orders of derivative for this function. So when you have a smooth function, it allows us to take first derivative, second derivative, third derivative, and so on and so forth. When you are able to take higher order derivatives and substitute 0 in place of the variable, you will be able to get a more accurate solution. And that is the reason why this approach works when we assume that our solution is the f of x solution is smooth. If not, this entire approach becomes restrictive. Now, let us consider what happens when, or what is the significance of x being 0 with respect to the functions being smooth. So what we essentially mean by the function being smooth and substituting the x0 here is, not in all places, but it is vital for us to have a smooth function at the position x0. So when we say that we have a smooth function, it is vitally important that the smoothness of the function is valid at x0, because that is where we are going to take the higher order derivatives. So of course, we expect a smooth function that allows us to approximate our function as a power series. But when the function is differentiable at specific positions, say x0, we will be able to ascertain these coefficients that are a0, a1, a2, and a3. So it's not that they are smooth, and they are smooth at a specific position. They are differentiable at a specific position. So in this case, in this starting point, so we are trying to build a tool, and at the starting point, we have an expression. We assumed that that expression is smooth and smooth at x0. Now what this often is not true, we can make this generalized. So what if my expression is not, it is smooth, but it is not smooth at 0, but it's smooth at a random point b. So I have an expression, I have a solution f of x, the solution is smooth, so my condition is satisfied. So I can use my power series expression as a starting point to solve or arrive at a solution. But my solution is not smooth at 0, but it is much more smoother, much more approachable at a specific point b. So how will my Taylor series expansion alter itself when I have such a condition? So this condition is a specific one, differentiable at 0. It's smooth at 0. I can have higher order derivatives at 0. I have a generalized case wherein I can take the higher order derivatives at B, a specific point B. So how will my Taylor series change? Now we will take the same approach that we have taken before. So basically what it means is, instead of x, we are now expressing my term as x minus b. So basically in the original case, my x represented x minus 0. This is what my x represented. My x square represented x minus 0, the whole square. My x cube represented x minus 0, the whole cube. Now that I'm no longer interested in differentiating at the point 0 or x0, but I'm interested in differentiating at xb, I can rewrite this entire power series as something like this, wherein my x's are x minus b, my x squares are x minus b the whole square, and x minus b the whole cube originally relates to that of my x cube in the original power series. Now once I have this power series expressed, arriving at or estimating, so this is the same approach that we have taken, estimating or translating this to that of the Taylor series. So power series to Taylor series translation takes up the same approach, wherein now instead of differentiating at x0, I'm differentiating and substituting my x with respect to b. I'm replacing my x with b. I'm taking the same route of understanding or ascertaining my coefficients by taking the derivatives, but now instead of taking the derivative and replacing my x with 0, I'm taking the derivative and replacing it with b. Taking the second derivative, replacing it, the x's with b. Taking the third derivative, replacing my x's with b. Taking the fourth derivative and replacing my x's with b. Now what I end up having is a generalized expression for a solution that is differentiable at any random point b. Originally, I had a solution that was differentiable at 0. Now I have a solution that is differentiable at any random point b. Now when you substitute your b to 0, you end up having, when you substitute your b 0 as 0, you end up having your original Taylor series. So in this session, so I would like to wind up the session here. So in this session, what we essentially have done is, we are trying to, again, our original goal is to try to solve expression of this form here. So we have, let's say, a second order ODE, we refer to the second order ODE. We want to solve an expression something like this. Now in order to solve that, we are trying to build a tool and we are getting our raw material. And that raw material begins with an assumption that my solution is going to be continuous now or smooth. Now what I mean my solution to be smooth is, my solution is differentiable at a particular point. I'm going to take my solution and differentiate it numerous times, and my solution every time is going to be differentiable. And this solution that is differentiable at a specific point allows me to calculate these unknown coefficients here. And that specific point can be any random point or it can be 0, and depending on what the nature of the point is, I end up having these description of Taylor series, which will help us solve this higher order ODE. I'm getting the raw material has given me Taylor series expansion, and now I will intend to use this Taylor series expansion to solve my equation. So this is where we will start in the subsequent lecture, and we will try to solve the expression. We will try to use this approach to solve the second order ODE. But before doing that, before getting into the actual solution, before solving the expression, we will see how relevant this Taylor series is in some of the functions that we are familiar with. We have talked about being continuous, we have talked about being able to differentiate at higher levels, and we have talked about substituting 0 in the most general way. We will try to take some functions that are known to us, try to apply these power series and Taylor series expansion, and we will see how relevant it is. We will get an idea for this Taylor series, we will get a feel for this Taylor series, and then once we have completely understood this Taylor series, we will use it to solve the expression. We will see ourselves, and we will try to begin where we left off in this next section.